Hi, I'm Jonathan Aldrich, and today let's talk about modules, names, and scopes. First of all, modules. Modules are an abstraction that groups a set of related entities together. For example, a common grouping is a data structure together with the functions that operate on it. We'll see that object-oriented programming captures this kind of modular structure in a very direct way. Now, modules provide multiple kinds of benefits. They provide abstraction. Abstraction allows you to understand a module in terms of its interface and just think about what it's supposed to do, not how it does it. This reduces cognitive load because you can look at one module at a time and just think about what other modules are supposed to do without looking at their detailed implementations. This is a kind of information hiding. What we do is we hide the internal representation of a module and private functions inside that module from the outside world. This enforces the integrity of data because that data can't be manipulated except by other functions in the module. It also makes it easier to find bugs or to change representation and algorithms because we know that no one from outside the module can rely on the exact representation of the data or the exact algorithms that we use. And we know that any bugs can be isolated in the functionality of that module must come from the module itself and not code outside. This also scopes names so that different modules can use the same name without conflicting. One person who is very significant in the historical development of modules is Barbara Liskov. She's a faculty member at MIT and a leading figure in the history of abstraction mechanisms. She designed Clue, which is one of the first languages to provide modules, which she called clusters. She's also the principal designer of the Argus programming language, which combined language and database technology to improve the reliability and programmability of distributed systems. Liskov received the ACM Turing Award in 2008. Let's look into modules in more depth. Module boundaries are important because they distinguish the inside of the module from the outside. Objects inside the module can see each other, and for example, functions inside the module can call each other or they can access data that's declared inside the module. On the other hand, objects inside the module may not be visible outside unless they are exported from the module. Similarly, objects outside the module might not be visible within the module unless they're imported. The idea of separate compilation relies on modular structure. The idea of separate compilation is that a module implementation can be compiled without the knowledge of other module implementations, and then later these can be linked together. Many module systems separate the interface of a module, which is sometimes also called the signature or the header of the module, from that module's implementation. This allows true separate compilation because you can compile the implementation of a module just looking at the signature of other modules. This is efficient because the signature contains typing information about those modules, so we can type check the module that we're compiling right now based on signatures of other modules. And it also contains enough information to know how to generate code to call functions from those other modules. That said, many practical systems only get partway there. For example, C's header files declare variables and functions before they are used, forming a kind of module interface. However, transitive dependencies can result in very long headers and resulting slow compilation for C and, in the same family, the C++ language. Java lacks separate signatures. Everything is just a Java file. But there's a semantic notion of a class signature that limits the files that a compiler must load, providing partial support for separate compilation. Let's talk about how scope is implemented. A symbol table is typically used to track information about names in a scope. The table maps names to information the compiler knows about them, such as their types, or perhaps in the case of compile time constant, what the constant value is. This allows some basic operations, such as inserting or updating a mapping from the name to the information about the compiler, looking at information about the name, looking up information about the name, and entering or leaving a scope. This creates the notion of a current scope, which is often used inside a compiler and naturally supports ideas such as nested scope and shadowing. Let's talk a little bit about the meaning of names within the scope. One concept that's important here is aliasing. This is when two names refer to the same entity. Now, the benefits of aliasing include providing a natural way to solve a problem, and in the presence of heap aliases, it can provide asymptotically more efficient algorithms. An example of that is the union find algorithm. On the other hand, there's drawbacks to aliasing. It can make optimization more difficult. In fact, Fortran even prohibits aliasing between procedure arguments. And for a long time, Fortran compilers could produce faster code than C compilers because they could take advantage of this assumption. Now, C has a modifier called strict that does the same thing and provides a similar performance advantage. Aliasing can also be confusing to programmers. It's easy to forget or not be able to figure out from the source code very easily what are the aliases of a name. And of course, then if we change data through one name, that will affect accesses to that same data through another name. And so this can feel like the data is changing without ever seeing why it's changing, right? Because the assignment might be in some distant part of the program. So aliasing has to be used carefully to avoid these problems. Another concept related to the use of names in a scope is overloading. Overloading happens when functions with the same name take arguments of different types. Almost every language overloads operators. For example, the plus symbol is used for integer addition as well as for real addition, or floating point addition is in practice. How do we know whether to do integer plus or floating point plus? Well, we look at the types of the arguments. So if we're adding two variables of type integer, then we'll use the integer plus. Typically, we'll treat the name, we implement overloading by treating the name as if it included the argument types. And in fact, in the early days of C++, which supported overloading, C++ was translated to C, which did not have overloading at the time. And so the C++ compiler at that time literally added the argument types to the end of the name in a technique called mangling in order to support calls that were explicitly to one version of the overloaded function or another version of the overloaded function. The idea is that the type checker can tell what the types of things are and therefore which function to call. Some languages, such as C++, support programmer-defined overloading as well. For example, here is a norm function that might return an absolute value of distance between a number and 0. The norm for just plain old integer numbers is just either a or the negation of a, whereas for complex numbers it might be a more interesting definition. By overloading, we can use the same name for the function, which is intuitive, but it will call either the integer version or the complex version, depending on whether we pass it an integer value or a complex value. Let's check our understanding.